Hello everyone and welcome. My name is Jason Gregerson. This video is going to be a video key of the practice exam for linear algebra MA2320. Alright, we're going to zip down to question number 1. I'm just going to talk through as I work through the exam. The important thing to remember is that you should try this exam first, the blank copy, and just work through the exam and check your time and all that kind of good stuff. After that, compare your answers to the key, and then reference the video for questions you're stuck on or you want to hear an explanation. This video will be longer than most videos, so it might be a little bit long just to watch all the way through. Alright, we're going to look first at the true and false. Given an n by n matrix A, label each of the following as true or false. And the first one says that a basis for R3 must contain exactly 3 vectors, and that is true. So the basis for R3 must contain 3 vectors, R4 are 4 vectors, and that number is fixed because the number of vectors in a basis is the same for any basis of a vector space. Next, B. If 0 is an eigenvalue, then the matrix is not invertible. So we kind of think about that eigenvector equation, AX equals lambda x. And the idea is that if 0 is an eigenvalue, well then our equation would simplify to this guy. And the only way that this guy can have non-zero vectors as solutions, in other words eigenvectors, is if A is not invertible. So this is also a true statement. If 0 is an eigenvalue, the matrix is not invertible. C is an n by n matrix A must have n distinct eigenvalues to be diagonalizable. So to be diagonalizable means we can take A and rewrite it as P times D times P inverse, where D is a diagonal matrix. Now our process for doing that forms P as the eigenvectors of the matrix as columns. And D, the diagonal entries, are the eigenvalues. Now, if we have n distinct eigenvalues, it is true that we'll have n eigenvectors, and we'll definitely be able to form P. However, we could have a case where we might have lambda equals 1, 1, and 3. So in other words, we don't have distinct eigenvalues. But if we plug in lambda equals 1, we might get 2 vectors in the basis for that eigenspace. In that case, we would still get 3 vectors, eigenvectors, and we would be able to form the matrix P. So this is not a requirement. So we might not have n distinct eigenvalues, but still be able to diagonalize A. That's why this guy will be false. D. Set of all solutions to the homogeneous equation, AX equals 0, is called the column space of A. That is incorrect. This should be the null space of A. So this one is false. E. If A is invertible, then the dimension of the column space is equal to n. So if A is invertible, then we have that long invertible matrix theorem that all the other things are true, and one of those things is true is that we must be able to row reduce to the identity matrix. We might be able to row reduce to the identity matrix. In other words, there's going to be a pivot in every row and column of A. Well, since the dimension of the column space is the number of vectors in its basis, and we would get the linearly independent columns to be the basis of the column space, then we can identify those columns that are linearly independent with pivots. So the fact that there's a pivot in every column tells me those columns are all linearly independent, and so I would use all of the columns as a basis, thus the dimension would be n. So this one would be true. If A is invertible, the dimension of the column space is n. F, the set of all solutions to AX equals B form a vector space for any vector B. This one is false. So the idea is the set of all solutions to AX equals 0. All those x's do form a vector space. We call that the null space. But the solutions to AX equals B do not form a vector space. Probably the easiest way to check that is to be a vector space, the 0 vector has to be included in that space. But A times 0 is not equal to some random B. Okay? A times 0 is only equal to 0. So 0 is not a solution to AX equals B for any B. Alright, we're past the true and false. Now we have number 2. It says let the following set of vectors be a basis for the vector space V. So they are giving us a basis for that vector space. The first question is, what is the dimension of V? Well, the dimension is just going to be 2, because the dimension of a vector space is the number of vectors in its basis. We have 2 vectors in its basis. The dimension of the space would be V. Then the next question is this vector in V? Well, if this is a basis for V, then I should be able to take a linear combination of the basis vectors and generate any vector that's in V. So if there is a solution to this equation, then yes, x is in V. And if there's not a solution, then no, x would not be in V. So in other words, to solve this, I'm just going to solve this vector equation. I can do that by setting up the augmented matrix and doing my row reduction, because I'm finding out if there are solutions to that vector equation. And so now I just do my row reduction. My first row I'm just going to leave the same here, and then I'm going to take R2 plus R1. I will get 0, 1, and 2. And I'll take R3 minus 2 times R1. I will get 0, 3, and 0 minus 2 times negative 3 should be 6. My next row operation is going to be row 3 minus 3 times row 2, in which case I'll get a row of all zeros here. And lastly, I'm going to take row 1 plus row 2. So my third row is going to stay the same. My second row is the same. I'm going to take row 1 plus row 2 to get 1, 0, and negative 1 here. So at this point right here, I would be in REF. And at that point, I would know that yes, there are going to be solutions. So yes, x is in the vector space. So I can check that box yes. But I see the next thing they want me to figure out is what the actual linear combination is to verify that it's in the vector space. So then I have to go to RREF and figure out what the solutions were. And it looks like my solutions in this case for C1 and C2 would be negative 1 and 2. So it looks like if I take negative 1 of the first vector plus 2 of the second vector, I should be able to generate that. And of course, once I write that down, I should try to verify that. And I can see that if I take negative 1 times 1 plus 2 times negative 1, I really would get negative 3. I can verify that for the other values as well. So it looks like my work is correct. Part C, it says what are the b coordinates of x? Well, the b coordinates are the coefficients of the basis vectors. The coordinates are how many of each basis vector do I need to get to the vector x. So in this case, I took negative 1 of the first vector and 2 of the second vector. So that would be the coordinates of this vector x in the b basis. And I would write that like negative 1, 2. And it makes sense that it only has 2 components because this is a 2-dimensional vector space. And I should have 1 component for each basis vector. All right, let's move on to the next one. Now I'm given a matrix A and I have a whole bunch of questions about the null space and the column space and the dimension of all that good stuff for this matrix. First question is, the null space of A is a subspace of what R space? Okay, so where do the null space vectors live? The null space is a subspace of what larger space? So our null space are the set of all solutions to AX equals 0. So if I were to put an example of a vector x here that I would multiply matrix A by to get to 0, it would have to have 4 components. Just for me to be able to do that matrix multiplication. That tells me the null space lives in R4. All those vectors live in R4. Now it says find a basis for the null space. Well, once again, it's the solutions to AX equals 0, so all I have to do is solve that equation. So in general, I would take this matrix A and do row reduction on it. However, I can look at this matrix and say that it already is in RREF. It already is row reduced. So in that case, I can just go ahead and write out my solutions. So I'm basically taking my matrix, augmenting with 0. In general, I would have to do the row reduction, but as I said, it's already done. And then once it's row reduced, I would write my solutions in parametric vector form. In this case, I get x1 is equal to negative x3. I get x2 is equal to negative 2x3. x3 looks like it's a free variable. I don't have a pivot in this column. And it looks like x4 is equal to 0. So in parametric vector form, it looks like negative 1, negative 2, 1, and 0. So that would be my basis for the null space. And the next question is, what is the dimension of the null space? Since I only have 1 vector in its basis, the dimension would be 1. And I should be able to verify that by looking at the original matrix as well. I should get 1 basis vector for every free variable. And so since my matrix was already row reduced, I could see that there was only one column with no pivot. That would tell me there's going to be one free variable, thus one vector in the basis of the null space. So I can check that, kind of double check that as well. Now we move on to column space. What is the column space of a matrix? It's the set of all linear combinations of the columns. Right? It's all the space I can build by combining the columns of the matrix A. So I already know that the columns span this space. So if I took linear combinations of all four of these columns, that would build the column space. However, to be a basis, I can only take the linearly independent vectors. So since I have a pivot here, here, and here, I'm only going to take those three columns. Now be careful, this matrix is already row reduced. If I had to do row reduction, the pivots would just tell me which columns from the original matrix to use for the base for the column space. So as I'm writing that out, I realize I've jumped to E here, but we can actually just use that to answer question D anyway. So I'm going to write down these basis vectors. They're going to look like this. And so if we go back up to D, it says the column space is a subspace of what R space. Well, all of our basis vectors live in R3. So our column space is a subspace of R3. And then F says what is the dimension of the column space? Well, once again, we have three vectors in its basis. So in this case, the dimension would be 3. The fact that the column space is a three-dimensional subspace of R3 tells us the column space is actually all of R3 in this case. Next question, question 4 has us calculate some determinants of the following matrices. So we'll start with a 2 by 2. And here we have to understand that we're taking the product of the strong diagonal, 4 times 1, minus the product of the off diagonal. That's minus a negative 2. Be careful with your signs here. Minus a negative is a positive, so here we're going to have the value 6. We look at the next one, and we could certainly do an expansion along a row or column, but we recognize this matrix is triangular, and therefore the determinant of that matrix would just be the product of the diagonal entries. So here we have 20 times negative 3, looks like a value of negative 60. Moving on to part C. Now we have a larger matrix, and it is not triangular, so we really have to expand along a row or column. And the trick is to find a row or column where there are the most zeros. In this case, I'm going to expand down column 3. Now, the first thing I'm going to do is set up all my signs. So starting in the top quarter, I got positive, negative, positive, negative, positive, and negative. And so if I'm expanding down that first column, I would have 0 times the submatrix, minus 0 times the submatrix, plus 2 plus negative 2. Make sure we have a sign there. Make sure we don't miss this little negative sign. So it's plus a negative 2 times the subdeterminant I get when I eliminate the row and column of that value. So the matrix I would be left with is 4, negative 1, 0, 0, 1, 1, and 1, 2, 0. And then lastly, as I finish expanding down that third column, minus 0 times some subdeterminant. So the reason I expanded down that column is because so many of these terms just go away because their coefficients are 0. But now I have minus 2 times this subdeterminant, and once again I'm going to want to expand down a row or column of this 3 by 3. So once again I'm going to expand down the third column. I got plus, minus, plus, and minus and plus. So it looks like as I expand down that third column, it's going to be plus 0 times something, minus 1 times a subdeterminant, 4, negative 1, 1, 2, and then plus 0 times something. So I'm going to get positive 2 times 8 minus negative 1. Looks like I'm going to get a value of 18 here. Alright, then we're moving down to question 5. Here we are given the diagonalization of a matrix A. So they are telling me that A is equal to P times D times P inverse. Now if they didn't tell me that, if I was just given A and had to calculate what the diagonalization was, my process would be to find the eigenvalues and eigenvectors. And then I would use the eigenvectors as the columns of the matrix P, and I would use the eigenvalues as the numbers on the diagonal entry of D. So because I understand that's how I would form P and D, I can just pull those values from P and D. So what are the eigenvalues? It is 4, 2, and 1. What are the eigenvectors? And here order matters. So in other words, the eigenvalue 4, because it's listed first in the first column, is associated with the eigenvector 1, 0, 1. And then the other columns of P would be the other eigenvectors. Now it says, part B says, use the information from the previous part to write an expression for a to the fourth power. And the idea here is that if I want a to the fourth, that's really a times a times a times a. But if it's diagonalizable, then I can simplify this, and we don't have to show this work in general on your exam, but all these inside values are turned into identity. Identity times d is just d. So this really simplifies to p times d to the fourth times p inverse. And the nice thing about that form is that because d is a diagonal matrix, I can really just raise the values on the diagonal to the fourth power. So I would write this out as 1, 1, 0, 0, 0, 1, 1, 0, 1, my matrix P, times D, but now I'm raising the diagonal entries to the fourth power. Make sure you put those powers inside the matrix so I really know that you understand how to raise the diagonal matrix to the fourth power. And then times our P inverse. So you don't actually have to calculate what a to the fourth is, just show me the expression for that, and this would be that expression. Alright, moving on to question 6. Now we're calculating eigenvectors, eigenvalues and eigenvectors, and actually doing the diagonalization if possible. So finding the PD and P inverse, or if we were to get complex eigenvalues and vectors, then we have to write the factorization PC P inverse. So I'll start by calculating the eigenvalues and eigenvectors. So step 1 is to use a minus lambda I, find that determinant and set it equal to 0 to find the eigenvalues. In this case, I'd have 2 minus lambda, 3, negative 1, and 6 minus lambda. I would then calculate that determinant by taking the product of the strong diagonal values minus a negative 3, so that's plus 3. I would then expand this guy out to get 12 minus 2 lambda minus 6 lambda plus lambda squared plus 3. Reorganize that to be lambda squared minus 8 lambda plus 15. And then I got to try to factor this guy. Looks like I can actually factor that one into, how about lambda minus 5 and lambda minus 3. Remember, if I can't see that, if I don't recognize that, I can always go back and use the quadratic formula. But I can see that. I'm setting that equal to 0. Tells me my eigenvalues are 3 and 5. 3 and 5. Then I have to find the associated eigenvectors. So now I got to say if lambda equals 3, for instance, now I got to solve AX. Now I have to solve my eigenvector equation a minus lambda I times x equals 0. So now I plug in the eigenvalue and solve the associated homogeneous equation. So if I subtract 3 on the diagonals, I get negative 1, 3, negative 1 and 6 minus 3, which is 3. I'm not surprised to see that they're multiples of each other. That's to be expected. When I row reduce this guy, I'm going to get a matrix that looks like this. First equation tells me that x1 is equal to 3x2, and x2 is my free variable. Looks like my first eigenvector is going to be 3, 1. Now I got to find my second eigenvector, so I'd say if lambda equals 5, well, then I plug that guy in, subtract 5 on the diagonals, I get negative 3, 3, negative 1, and 6 minus 5, which is 1. Once again, not surprised that they're multiples of each other. This guy is going to simplify to this form. My equations are going to be x1 equals x2, and x2 is free. Looks like my second eigenvector is going to be 1, 1. So now I have to form the matrix P and the matrix D or C, depending. So my matrix P is going to have columns that are the eigenvectors. So when lambda equals 3, my eigenvector was 3, 1. When lambda equals 5, my eigenvector is 1, 1. And in this case, because my eigenvalues are real numbers, not complex, I'll form a matrix D, whose diagonal entries are the eigenvalues. Once again, being careful of my order. Now I go to the next problem. Same problem. In this case, I can take a little bit of a shortcut because I see this is a triangular matrix, so I can know my eigenvalues right away are 2, 1, and 1. Now I want to calculate the associated eigenvectors. So I'll say if lambda equals 2, I'll subtract 2 on the diagonals. I'll get 0, 1, 0, 0, negative 1, 0, 0, 0, negative 1. Augmenting this with 0 and doing my row reduction, I will have zeros for the second row, and I'll change the sign of the last one. One more step here, just switching the order of the second and third rows. This one tells me that x2 is equal to 0 and x3 is equal to 0. Looks like in this case x1 is my free variable, so it looks like my first eigenvector is going to be 1, 0, 0. Now I'm going to plug in if lambda equals 1, and because 1 has a multiplicity of 2, I'm a little nervous because I'm going to need to get 2 eigenvectors for me to actually be able to form a matrix P. If I only get 1 eigenvector, then this matrix would not be diagonalizable. Well, when I plug in lambda equals 1, I'm going to get 2 minus 1 as I subtract my eigenvalue on the diagonals to get 1, 1, 0, 0, 0, 0, and 0, 0, 0. So this one's already in row reduced echelon form. My first equation would give me x1 is equal to negative x2, and it looks like x2 is a free variable and x3 is also a free variable. x2 is a free variable and x3. So if I was writing this in parametric vector form, I'd have one vector with x2 stuff, negative 1, 1, 0, and one vector with x3 stuff, which would be 0, 0, 1. So in this case, the dimension of this eigenspace is 2. The geometric multiplicity is 2, the same as the algebraic multiplicity. So it is diagonalizable. So to form the matrix P, I'd first put my eigenvector associated with lambda equals 2, and then I would put my 2 eigenvectors associated with lambda equals 1. Then I'd form my matrix D, 2, 0, 0, 0, 1, 0, 0, 0, 1. Eigenvalues on the diagonal entry. So I have finished part B. Now finally I look to C. Honestly, I'm looking at part A and seeing I got some real values, part B got some repeated values. I'm really expecting some complex values in C. Let's see what we get here. So first I'm going to calculate my eigenvalues. I'm going to go 5 minus lambda, negative 10, 1, and negative 1 minus lambda. I'm calculating the determinant of this. I got 5 minus lambda times negative 1 minus lambda. Minus a negative 10 is plus 10. Be careful with that sign right there. Then I expand my value here. I get negative 5 minus 5 lambda plus lambda squared plus 10. This guy is going to simplify to lambda squared minus 4 lambda and plus 5. And this guy is equal to 0. I'm going to set this equal to 0. So now I'm looking at the factors here. Boy, I think 5 times 1, if I add or subtract those, I should get to 4. But because my sign is positive, it's got to be negative 5 times negative 1 or positive 5 times positive 1. Neither of those I can manipulate to get to negative 4. So it looks like I can factor it, but it doesn't. But I actually can't. So you got to be super careful of that, because if you accidentally factor it incorrectly to get real eigenvalues, it really changes the problem. In this case, I can't factor it. I'm going to have to use my quadratic formula to say lambda is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Right? So that's what I got here. And then what am I going to have? Well, let's see. 4 over 2 is 2. Plus or minus 16 minus 20 is negative 4. The square root of that is going to be 2i. Divided by 2 is going to be plus or minus I. So my eigenvalues are 2 plus or minus I. Okay? So I have complex eigenvalues. Now I'm going to choose lambda is equal to 2 minus I. I'm going to choose that minus I value. I'm going to plug that into and subtract that on the diagonals. So I will get 5 minus 2 minus I. Minus 10 here, 1 and minus 1 minus the quantity 2 minus I, augmenting with 0. Now I certainly could try to do the row reduction, but it will be tedious because I'll have to multiply through by complex conjugate values to try to put real numbers in the same columns and then do that row reduction, and it's a pain. However, because this is a 2 by 2, and I've chosen lambda, so there will be non-zero solutions to the homogeneous equation, I know that there'll be free variables in this equation, which means I know these two rows are multiples of each other. that tells me that I could use one row to eliminate the other. I am going to choose to stick with row 2. It's a little easier to work with. So I will just write row 2 and simplify it a little bit. This will be minus 3 plus I. And then I would use that row to eliminate the other row. Right, so my knowledge helps me simplify this quicker to this form. And then I write out the associated equation. In this case, I have x1 is equal to 3 minus I times x2, and x2 is my free variable. So if I were to write this out as a vector in parametric vector form, I'd have 3 minus I and 1, and that would be my eigenvector. So my eigenvectors now are 3 plus or minus I and 1. Because I know that if I use the conjugate eigenvalue 2 plus I would get the conjugate eigenvector, which would be 3 plus I and 1. Now what about the diagonalization piece here? Well, in this case I can't diagonalize, but I can factor this into the form P, C, P inverse. And I just got to figure out what P and C are. Well, C is going to be a matrix that looks like A minus B, B, and A. So where A and B are the real and imaginary parts of the eigenvalue. So in this case, my matrix C is going to be 2 minus 1, 1, and 2, where I'm pulling A minus BI here. So A minus BI. So A is 2, B is 1. The matrix P comes from the real and imaginary parts of the eigenvector. So here is the eigenvector associated with the eigenvalue that I chose. I chose lambda equals 2 minus I. I have to use the vector associated with that. That's 3 minus I over 1. And the first column of P is the real parts. That is 3 and 1. And the second column of P are the imaginary parts. In this case, that would be negative 1 and 0. So now I have formed the matrix P, and I have formed the matrix C, such that A is equal to P times C times P inverse. Alright, that zips through the rest of the exam. So hopefully on the actual exam you have a little more space to work through these problems. Some of the formatting might be a little different. These will be all the core questions on the exam. You should also practice a couple application problems, but for the most part this is going to be the core content. If you have any questions, make sure you reach out. Alright, thanks for your time.